Hello, everyone, and welcome to Kshitij Goyal's Ph.D. thesis defense. He will be talking about his work in communication deficient active reconstruction using self-organizing Gaussian mixture models. I just ask that you please hold your questions until the end of the talk. And with that, take it away, Kshitij.
Thanks. Hello, everyone. Welcome to my PhD thesis defense. Today, I'll be defending my work on communication efficient active reconstruction using self-organizing Gaussian mixture models. The problem statement considered in this thesis is as follows. We consider a team of robots operating in an unknown environment where each robot is equipped with a depth sensor. Within this setting, there are four main objectives. First is to autonomously gather point cloud data in this environment as the robots are moving. Second is to make a model of these observations that can be used for tasks like collision avoidance and reconstruction. Third is to share these models amongst robots to improve the reconstruction speed. And lastly, the robots are not allowed to collide with each other or to the environment. Reconstruction is quite valuable in many real-world applications. Here are some examples. First is for reconstructing environment features from depth images. For instance, in this plot, the reconstruction is used to monitor canopy height in dense forests. Second is towards accurately preserving historical monuments, such as this work where authors used a team of aerial robots to reconstruct interior of a historical building. Another one is towards tasks like surface reconstruction using rovers on other planets. And lastly, towards enabling personal home robots, reconstruction is used to create data structures like scene graphs. To meet the stated objectives for this problem, we want to make a map representation that addresses three key challenges. First, the representation must enable reconstructing the sensor observations while being small enough to transfer to other robots. This is challenge one, communication efficient reconstruction. Second, the same representation should be useful to avoid collisions amongst the robots and to the environment. This is challenge two, collision avoidance. And lastly, the representations learned by individual robots should be useful to expand the representation further by autonomously gathering even more data. This is challenge three, multi-robot informative planning. So how do we go about creating a representation that can address these challenges simultaneously? One choice is to use raw point cloud data. However, these point clouds can be quite expensive to communicate relative to things like motion plans, which are relatively inexpensive to communicate. For instance, if you consider a depth sensor like the D455 from Intel at 60 Hertz, 640 by 480 resolution, it generates about 18.5 million points per second. And that's about half a gigabyte per second of data being generated. It is evident that if we use this representation for the active reconstruction problem, we will likely run out of usable memory on board the robot. To this end, in this thesis, we hypothesize that using Gaussian mixture models to represent point cloud data, we can do communication efficient reconstruction by adaptively compressing point clouds. We can estimate collision risk and enable inter-robot and robot environment collision avoidance. And finally, we can use the same representation to perform distributed mapping that can help with multi-robot informative planning. For adaptive point cloud compression, we introduce a method called self-organizing Gaussian mixture modeling, or SOGMM for short. This method compresses point clouds into a GMM. And from this GMM, the original sensor point cloud can be reconstructed. An example of one such reconstruction is shown in this video. Second contribution is towards solving challenge two. This time we use the GMM model to calculate Euclidean distance between the robots and the environment model. An example of the Euclidean distance field is shown here. Lastly, this thesis contributes a system that enables distributed mapping using GMMs. This distributed mapping system can be used for active multi-robot reconstruction in challenging environments like caves, such as the one shown here. It is important to talk about why we are choosing Gaussian mixture models for this purpose, because there's plenty of prior work on creating compressed point cloud models. Most popular ones are explicit methods, where the representation is often a set of 3D locations over which some set of features like occupancy and color are stored explicitly in memory. In order to achieve a compression, the 3D locations are often arranged in a tree data structure. The most popular one is the octree. These approaches can provide reconstruction capabilities. However, the intensity value in each 3D cell is set naively by averaging averaging intensity values in the nearby cells. Therefore, while these models are useful for tasks like collision avoidance, reconstructing features via these models is quite inaccurate. Towards achieving more accurate reconstruction, truncated sign distance fields have been used in practice. The idea is to maintain a TSDF over time for accurate surface reconstruction, and then interpolate a distance field for robotics applications like collision avoidance. Unfortunately, the map sizes are quite high in this case, since the cell size has to be kept small in order for the interpolation to work well. In a nutshell, there's no sense of compression in 3D space for these approaches. Towards addressing the limitations of explicit methods, implicit representations were developed. In this case, the model is a function as opposed to a set of 3D locations. The function can provide value of features like occupancy, color, sign distance, radiance, and so forth in the continuous space as opposed to discrete space. Gaussian processes and neural networks are two primary types of implicit representations that have been explored for robotics applications. For Gaussian processes, the state-of-the-art methods provide collision avoidance capability via continuous distance fields. The reconstruction accuracy is generally higher compared to explicit methods. However, it is unclear how to use GPs for active multi-robot reconstruction problem considered in this thesis. For neural networks, typically a multi-layer perceptron is used as a representation. Reconstruction with multiple robots is known to be possible through a recent work, which shows reconstruction using 3 robots. However, in this case, the overall limitation is due to the fixed MLP architecture. All the robots used fixed number of layers and fixed number of neurons for every possible environment. Ideally, we want the architecture to be flexible and adaptable to the kind of environment the robots are observing. Given the downsides of both implicit and explicit methods, there has been a significant effort on getting the best of both worlds via Gaussian mixture models. In this case, the representation is approximately explicit. We can view the model as a set of ellipsoids in the ambient space. While simultaneously, the model has an implicit definition. It is a probability density function. In this direction, NDT map was one of the first 3D representations proposed for robotics applications. The idea here is to use a Gaussian distribution in each cell of a 3D grid, and then use this Gaussian distribution for maximum likelihood updates. However, due to the grid structure, it suffers from the same problems as the TSDF work. Recent works have proposed removing the grid structure. These approaches use Gaussians on both surfaces and in free space, but the Gaussians are not confined to a grid structure. While these methods provide considerable improvement over NDT map and other grid-based methods, the focus is on modeling occupancy as opposed to the quality of reconstruction on the surface. Towards enabling higher quality surface reconstruction using GMMs, follow-on works have largely used image space projection, popularly called splatting. There are several methods on this front. One approach is to use maximum likelihood updates as done in NDT map. But here we apply these updates at a pixel level by projecting 3D Gaussians to the image space. The downside of this approach is that intensity variation per Gaussian is not considered. Therefore, to model intensity accurately, a lot more Gaussians have to be used. Another recent method is to make the image space projection operation end-to-end differentiable via a powerful rasterizer. In this case, GMM parameters are adjusted via Adam optimizer as opposed to maximum likelihood updates. Here, the intensity is determined using alpha compositing as it's done in graphics applications. Typically, this approach requires a high number of Gaussians, such as this work by Tao et al. Since the original Gaussian splatting approach was for monocular data, recently Tao et al. Proposed a work where they use depth and ground truth pose data for active reconstruction using Gaussian splatting. We observed that the reconstruction quality is quite inaccurate because of a problem that's informally called floating Gaussians. These Gaussians are incorrectly placed in the environment and then rendered via splatting, resulting in incorrect intensity values. Unsurprisingly, we observe the same problem in the offline reconstruction as well, where the Gaussians are floating under the floor or in front of the camera. Moreover, despite significant advances over the past year or so, to the best of our knowledge, there is no Gaussian splatting-based method that directly addresses the problem considered in this thesis. In contrast to these methods, the contribution of this thesis do provide a multi-robot reconstruction approach. The outline for the remainder of this talk is that we will go through these contributions one by one. Starting with contribution 1 for adaptive point cloud compression, we'll go through it in two pieces. First is the compression algorithm itself that converts the point cloud to a local GMM. And second piece is to create a global GMM out of a set of local ones as the robot moves in the environment. We consider a point cloud to be an unordered set of points, and each point is in 4 dimensions. The first 3 dimensions are position, and the last dimension can be a feature. And this feature we assume to be normalized to a range of 0 to 1. The task is to compress the point cloud, Z, into a 4-dimensional Gaussian mixture model given by a probability density function containing m number of components, which is the model complexity for the GMM, weights, means, and covariances in the 4 dimensions. Typically, if given a point cloud like this, which has 4-dimensional points, if you set a value of m high enough, you'll get a good enough fit for the model. So these are ellipsoids corresponding to the fitted Gaussian mixture model. However, in this thesis, we want to answer the question of how to automatically determine m and adapt it based on the scene complexity. In classical statistics literature, log likelihood scores are used for this purpose. Log likelihood is the score that determines how well does the data align with the model. There are 2 key approaches here. The AIC score, which minimizes the negative log likelihood and the size of the model simultaneously to figure out a good balance between the size of the model and how accurate the model is. The other approach is BIC and minimum description length, which are a variant of AIC, but with an added term to make sure that compression is done only when there's enough evidence. The problem with these kind of approaches is that you have to iterate over several values of m, which means you have to iterate over several models. And calculating these criterion values is expensive for each value of m. So we want to find m without testing several models and doing expensive log likelihood calculations. So the answer to this question is to find locally dense regions or modes in the dataset by iteratively moving samples in the dataset. This principle is called the principle of relevant information. Consider a dataset in 2D, dataset Y. We assume that each of the red dots here are IID samples corresponding to an unknown density Py for a random variable Y. Our objective is to find modes in this dataset given by the sparse set of points, red points. That's a separate data set YR. And these are IID samples from an unknown density PYR corresponding to a different random variable. The objective of principle of relevant information is go from left to right by minimizing Renier quadratic entropy and Cauchy-Schwarz divergence. Really what these terms mean is that quadratic entropy makes sure that there is less redundancy in the data, which means it is the compression term. And the Cauchy-Schwarz divergence term makes sure that there is less amount of error after compression. Notice that in this case, there's no iteration on several m values. The value of m should come out naturally from the data set. So how do we proceed solving this problem? First, we have to assume a density function py. In this case, we assume a kernel density estimate with the bandwidth parameter that is user modifiable. Then we substitute expressions for entropy and divergence, differentiate this function, and it turns out this becomes the Gaussian mean shift algorithm, which is quite popular in non-parametric statistics. To visually see how this algorithm works, we have a data set on the right-hand side, which is a bunch of gray points, and intuitively we can tell there are 4 modes in this data set. Mean shift algorithm takes a bunch of seeds on top of this data set and iteratively converges to the modes of this data set. In our work, we use these set of modes to initialize our Gaussian mixture model approach for point cloud modeling. Finally, when these modes are done, we get the clusters. So essentially what we are doing is we are initializing our parametric approach via a non-parametric initializer. If we focus on one sample, in this case, such as this red dot, and trace out the trajectory it takes while going through mean shift algorithm, it turns out that this is an adaptive gradient ascent algorithm. And the nice feature about this algorithm is that we do not have to set a fixed step size, which allows this algorithm to be quite general in application. We call our approach self-organizing Gaussian mixture models because the context in which the principle of relevant information was proposed, they called it self-organizing unsupervised learning approach. So we borrowed the term from there. We start with a pair of intensity and depth images. We convert this point cloud into a 4D point cloud, 3 for spatial and 1 for feature. Then we put the images through PRI and get the number of components M. Then using the 4D point cloud and number of components, we perform an initialization step and then expectation maximization to get the final Gaussian mixture model of the point cloud. Let's see how this works. On the left, we see 2 images, A and B. The variation in depth and intensity data in image A is relatively lower than image B. So we expect the method to yield higher number of components for image B compared to image A. That is what we observe in practice. On the x-axis, we have the bandwidth parameter, and on the y-axis, we have the number of components in the GMM. We observe that the red line in this image, which corresponds to the number of components estimated for image B, is always above the blue line in this image, which is the number of components estimated for image A. This leads to 2 observations about the model. First is that no matter what bandwidth parameter value you set, the estimated model complexity for image B is always higher than image A. And second is that the bandwidth parameter can be controlled to adjust the level of adaptive compression as opposed to the level of compression. In prior work, there are parameters that control the level of compression globally. But in our case, the parameter is used to control the level of adaptive compression. Next question is, how do we reconstruct from this model? We have figured out how to compress the point cloud model into a GMM, how do we reconstruct from it? So the compressed point cloud model is a 4D GMM. We take a spatial marginal out of it and densely sample it to get 3D locations. And then using these 3D locations, we take the intensity conditional and calculate the intensity reconstruction. So this process is quite straightforward once the Gaussian mixture model is constructed. Here are some examples of the reconstructions obtained through the proposed approach on grayscale point clouds. From left to right, the amount of variation in depth and intensity values is increasing as the expected number of components M also increase. The proposed approach clearly adapts the complexity of SOGMM as the complexity in the scene increases. Another feature of the proposed approach that it can work for both data like grayscale values and thermal values. This video shows reconstruction obtained for an outdoor thermal LiDAR scan of a building. We have seen so far how to compress a single point cloud into a GMM. Now the camera has to move and we have to incrementally create the SOGMM from streaming RGBD data. For this, we have to maintain 3 data structures. First is a local SOGMM, which is the SOGMM that you construct for a new observation. Second is global SOGMM, which is summarizing all the past observations. And third is a spatial hash that encodes the indices of global SOGMM with every 3D location. The key idea here is to use log likelihood scores and these data structures to perform incremental mapping. So given a point cloud that has just arrived from the sensor, we first use the spatial hash to associate it with global SOGMM. This gives us all the indices in the global model that are currently overlapped by the incoming point cloud. Then we filter this point cloud based on log likelihood scores to figure out which part of the point cloud is new compared to prior model. On this new part of the point cloud, we construct the Gaussian mixture model, and then we merge it with the global model that we have seen so far. And using this global model, then we update the spatial hash for the next iteration.
Just a quick clarification, the numbers in the red grid, those
3D
what are those values?
3D locations.
It's a depth value.
Yes,
The centers?
3D point. Yeah, centers and sigma points. Points at sigma levels of Gaussians.
Okay.
Let's see this method in action. In this video, the points in the red are the ones that are considered novel. The reconstruction from the learned SOGMM is shown via the grayscale point cloud. As the sensor moves in the environment, the SOGMM model is built incrementally using the approach that we just saw, leading to an accurate spatial and intensity reconstruction. There's the final reconstruction output for that run. We compare the proposed approach with Octomap, NV blocks, and a prior GMM-based approach for multimodal data that uses fixed number of components. The performance measures are towards assessing the reconstruction accuracy and map size. For spatial reconstruction accuracy, we use the precision and recall scores, while the intensity reconstruction accuracy is measured by peak signal to noise ratio. For the map size, we serialize the map data and store on disk in a binary format, and then we measure the size of that file in megabytes. Simulated and real-world datasets from Zhou et al. Are used for comparison. Snapshots of these datasets are shown on the right. We first qualitatively compare the reconstruction fidelity between these models. On the left, we have ground truth snapshots of the synthetic and real datasets. To ensure a fair comparison, the parameters of each approach are chosen in a way that the map sizes on disk are in a similar range. These parameters include minimum leaf size for Octomap, voxel size for NV blocks, number of Gaussian components for the FCGMM approach, and the bandwidth parameter for the proposed approach. Let us zoom in to part of these environments to understand the differences in reconstruction. These two images on the left are the ground truth values. For Octomap, we observe a good spatial reconstruction, but inaccuracies in intensity reconstruction. If you compare the ground truth images, the intensity values are miscalculated in some of the voxels, such as the floor and the sofa in the top image. This is expected because the intensity values are not jointly modeled with spatial data in this case. These values are set by averaging nearby cells. For NV blocks, we observe a smooth output compared to Octomap. This is because the method uses truncated sign distance fields and interpolation for reconstruction. However, if you observe the pillows on that sofa in the top image and the chair in the bottom image, they are not quite accurate spatially. This is because this method realistically requires small voxel sizes to leverage high accuracy interpolation. Next, if we set fixed number of components and follow a GMM-based approach, the spatial reconstruction performance is noisy. This is because it is not necessary that using a value of 400 components will be enough for every part of the scene. In contrast, the proposed approach provides adaptivity in the number of components and significantly improves the quality of reconstruction compared to these methods. Just to note, in this case, the FCGMM totaled to about 80,000 Gaussians, whereas the proposed approach was less than half, to about 35,000 components. This shows the utility of adaptive compression enabled by the proposed approach because it only puts higher number of components in regions where they actually need it. Quantitatively, here are two plots showing the variation of quality of reconstruction with map size. On the left, higher precision scores mean improved spatial reconstruction quality. On the right, higher PSNR values indicate better intensity reconstruction quality. We observed that in intensity reconstruction, even for the same amount of memory, the proposed approach shown in pink can provide a higher quality map compared to fixed component approach shown in green. Meanwhile, to achieve similar quality, methods like NV blocks can require over 100 times more memory than the proposed approach. The takeaway here is that SOGMM method requires less disk space and communication bandwidth and demonstrates better reconstruction accuracy than prior methods. And also, there is no need to declare a fixed model complexity for every scene. The method adapts to the scene complexity. So this was the first contribution of this thesis, where we proposed the SOGMM approach for adaptive point cloud compression. The key idea was to use the principle of relevant information to estimate number of modes in the dataset and adapt the complexity of the model. Using the k-means and EM algorithm, the final GMM can then be learned using PRI. And the final GMM can then be used to reconstruct spatial and intensity information. Let's move to the second contribution of this thesis, where we study the problem of calculating the collision risk of robots in the continuous space, given the obstacles in the environment are modeled using the GMM approach. The problem statement is as follows. The spatial marginal from the SOGMM method provides a set of ellipsoids as surface GMM. We consider the robots in the environment to be enclosed with ellipsoids, as ellipsoidal fits generally provide better approximation for robot body to plan paths that can go through tight gaps. Consequently, the future states of robots are also considered to be a set of ellipsoids. To avoid collisions between the robots and the environment, we have to find the collision risk between a set of ellipsoids. And to avoid collisions between robots, we have to find, again, the distance between a set of ellipsoids. So realistically, this problem boils down to getting distance estimates between a set of ellipsoids And then we can solve both problems, getting collision avoidance between robot and environment and collision avoidance between robots and robots. Unfortunately, there is no collision closed form solution to this problem. So we adopt a conservative approximation first proposed by Ryman and Boyd. This approach computes 2 points, x star, which is on the set of green ellipsoids on the left, and y star, which is on the set of red ellipsoids. Distance is simply the norm of the vector between them, and gradient is the vector from y star to x star. In practice, the distance values are tight conservative upper bounds in this case. And since the approach operates on individual ellipsoids, it is fast and parallelizable. Here's an example showing distance values of an ellipsoidal robot on a 2D grid of locations from a real-world point cloud modeled using Gaussian mixture models. So distance values increase from blue to red. Qualitatively, this distance field seems reasonable to use for collision avoidance. Regarding the computation time for collision avoidance, we are interested in calculating the time taken to compute distance and gradient per ellipsoid pair. We consider various CPUs that are commonly used for onboard computation, a laptop-grade i9 processor, which can be used on board grounded-legged robots, and 3 embedded CPUs from the NVIDIA Orin series of platforms, the AGX, NX, and Nano, with decreasing levels of compute. In the first column, we have the time taken to initialize ellipsoids. This step is only done once per ellipsoid pair to cache properties like rotation and scale matrices. The actual computation of distance and gradient is in the second column of this table. Note that these times in the table are shown in microseconds on a single thread of CPU and averaged over 100,000 random ellipsoid pairs to make sure there's no issue. From this table, it is clear that on a per ellipsoid pair basis, the computation is in few microseconds, even on embedded computers like the Nano. Since we have benchmarked this on a single thread of a CPU, it should be efficient enough for motion planning on CPUs as well as parallelizable to scale on GPUs if there's a need for it. Additionally, we do an accuracy comparison with state-of-the-art Gaussian process-based method that provides accurate continuous space distance fields. This method is chosen as a baseline due to its superior performance over other implicit methods and grid-based methods like Voxflux. The performance measure for distance field is the root mean square error between the ground truth and predicted distance values. While for the gradient, it is the error in alignment of gradient vectors, also known as cosine error squared. Here's a visual comparison of the error in distance field. The error is higher in the regions that are shown in red compared to yellow. On the left, we observe that in the baseline approach, we incur a higher error compared to the proposed approach on the right. We also ran an ablation study on different parameter settings of the approaches for both simulated and real-world datasets. For the baseline approach, the free parameter is called the length scale parameter. Lower length scales provide higher accuracy in GP-based methods. And for the proposed approach, this is the bandwidth parameter, with the lower bandwidths providing higher accuracy. We observe overall that the proposed approach provides comparable accuracy for both distance values and its gradient, but with an advantage that the proposed approach does not require access to the raw point clouds. We do distance and gradient computation using the ellipsoidal representation as opposed to the raw point clouds. In summary, through this contribution, we reduce the problem of collision avoidance between robots and the environment to problem of finding distance values between a set of ellipsoids. We then developed an approximate but efficient solver based on prior art on ellipsoid distance calculations that runs in a few microseconds per ellipsoid pair. And in comparison to state-of-the-art GP-based methods, the proposed approach does not require access to raw point clouds to achieve distance value calculation at high accuracy. That was contribution 2. So we now move to the third contribution of this thesis, which is towards enabling distributed mapping using GMMs, and then using those distributed maps for multi-robot informative planning. In this case, in addition to the collision avoidance problem, we have to share representations between the robots over potentially low bandwidth communication channels. We also have to share plans amongst the robots to perform collision avoidance, and then pick actions that increase the knowledge about the surface in the environment. In terms of sharing map representations in this thesis, we assume that the robots are perfectly localized. In this case, the red robot creates a model shown by red ellipsoids on the bottom left. We can apply the relative transform between the robots to obtain the GMM representation in the green robots frame, shown on the top left. Top right. The blue rays represent the original sensor observation as taken by the red robot. Note that this approach to distributed mapping only requires us to transfer Gaussian components as opposed to the raw point cloud or grid-based representations. This is the key aspect of this thesis that enables communication efficiency. For informative planning with these models, we first create a local occupancy grid from the GMM in a local submap around the robot. This ensures that our memory usage is lower compared to creating a global occupancy grid. And then using this occupancy grid, we perform motion primitives-based planning. We first generate a library of motion primitives around the robot position, as shown on the top right. And then using collision avoidance, we filter down these actions and pick the best action using an information theoretic reward. Note that we can use any volumetric information theoretic reward in this case. We just picked this one. Anytime operation is possible via Monte Carlo tree search. To analyze the effectiveness of the distributed mapping strategy, we set up simulation experiments with multiple simulated quadcopter vehicles that are equipped with TED cameras and can perform distributed mapping via the proposed approach. We also compare against a regular grid-based approach. We artificially constrain the bandwidth over a simulated UDP connection. So if we exceed the connection bandwidth, the transmitted packets will be dropped in the worst case. We test 3 settings. First, there are no limits on the connection. And then there are limits 0.25 megabit per second and 0.1 megabit per second. These limits are chosen so that they are quite low compared to the regular Wi-Fi or LTE connections. For context, a typical Wi-Fi connection is 100 megabit per second. The first limit is 400 times lower than that, and the second limit is 1,000 times lower than that. The performance measures here are the amount of map that may get dropped due to communication limits and the rate at which the environment is being reconstructed by the robot team. We do not want map to get dropped due to communication limits because we want the robots to have the latest information, and we want the rate of reconstruction to be high. Next, we can plot the cumulative amount of data transferred between any 2 robots against the reconstruction progress on the x-axis. When there are no limits on the bandwidth connection, one observation is that there's nearly an order of magnitude difference between the amount of data that is transferred between robots. The blue solid line here is showing the amount of data sent when occupancy grid maps are used, and the red lines show the same for GMMs. Both approaches are sending and receiving same amount of data when there are no limits, which makes sense. But when we constrain the bandwidth in the middle to 0.25 megabits per second, we observe that packets are lost in the occupancy grid case. The received packets are far below the sent packets. In contrast, the GMM approach remains unaffected due to this level of bandwidth constraint. If we constrain the bandwidth further, we observe some amount of packets on the GMM map front being dropped, but not as much as the occupancy grid mapping case. The takeaway here is that GMMs can enable efficient map transmission under bandwidth constraints. Next, we look at the time taken by each of the approaches to achieve a certain percentage of reconstruction versus the amount of communication constraints that we have imposed. And we observed that GMM approach consistently outperforms grid-based approaches. The delta columns here denote the percentage increase in the rate of reconstruction due to the GMM approach. The gain in performance is observed to be as much as 24% in some cases. Therefore, we observe improvements in reconstruction rate due to efficient transmission of maps. We also deployed this system on 2 real-world robots with a depth sensor equipped with an IR emitter and a global shutter camera that provides depth estimates even in low light scenarios. And we used a visual inertial navigation system for state estimation, assuming state estimation is perfect. The environment where this work was deployed is shown on the right. You can see a lot of clutter and complex obstacles that the robots must avoid, and at the same time reconstruct the environment. Here's the deployment video. On the top left, we are seeing reconstruction in real time, as seen on a base station within the environment. On the top right, there's the actual flight video as captured from a helmet camera of one of the operators. And we can see dense reconstruction from 2 robots in a wild cave from these robots. To summarize, in this contribution, we presented a distributed mapping approach that leverages GMMs under a perfect localization assumption. And we demonstrated several benefits of this method over the grid-based approach, including operation under bandwidth constraints. We started out with the hypothesis that to create a multi-robot active reconstruction system, we can use GMMs as a map representation to enable communication-efficient reconstruction, collision avoidance, and multi-robot informative planning. To this end, this thesis contains 3 contributions. First is self-organizing Gaussian mixture modeling, which presented an adaptive point cloud compression model, where the spatial and intensity reconstruction accuracy is much higher than prior works. Second was the collision avoidance approach, where the robots were constrained to avoid collisions with each other and the environment via the GMM-based approach. And lastly, we used the same representation to enable distributed mapping and informative planning. There are several promising directions for future work. One of them is to shift from volumetric mapping, where we model free space explicitly, to surface-only models for robotics applications. Currently, the only place we use a dense grid is for local informative planning. This is ongoing work in our lab. In this video, the robot is moving in the environment while performing next best view planning without local dense grids. So the robot is avoiding collisions with the environment and selecting next best action without any local dense information. However, there's a challenge that remains to be solved here. In this thesis, we considered how to model the occupied part of the environment. However, more generally, we need to maintain a boundary between known and unknown space. There would be several benefits if we can do this. First is that we will lower the memory usage even further. We do not have to allocate memory for free space at all. We can then use these resources to more rich surface representations, like incorporating semantics via segment anything model or incorporating language via clip models. Some work has already begun on this front. There is a recent work by Kin et al. that proposed a framework called LangSplat, where a 3D Gaussian-based representation was connected to the clip model to enable text-to-object queries in environment representation. Then there's another work by Maggio et al. That used the segment anything model along with the clip model to enable recognizing various objects and types of rooms in which the robot is navigating. These works may especially be useful in creating environment representations for home and personal robotics applications. Another direction is towards enabling robust localization using the GMM representation. There are several ideas in existing literature for this. There is frame-to-frame registration using mixture models that can enable local sensor pose estimation. Then there is loop closure capability to correct for sensor drift, again using the GMM representation. Then there are Gaussian splatting-based ideas that incorporate sensor pose tracking as part of the loss function, in addition to minimizing photometric errors. SPLATAM and GSLAM are two methods that are recent examples of this. Then towards incorporating loop closure into Gaussian splatting-based maps, there is a recent work called loop splat. The question of which of these methods for pose estimation to use really boils down to the intended application. To conclude, if we take a step back and look at the contributions of this thesis, the directions of future work, and the recent advances in using 3D Gaussians for computer graphics, it may be possible that the Gaussian mixture models are used in future robotics applications that are beyond the multi-robot reconstruction problem considered in this thesis, which is quite exciting. Before concluding this talk, I want to acknowledge my co-authors, Winnie, Nate, John, Micah, Janae, Eve, Alex, and Kurt, for several contributions to this thesis. I want to especially thank my thesis committee, Winnie, Nate, David, Basti, and Kostas, for feedback on several aspects of this thesis. Part of this thesis was sponsored by the Carnegie Mellon Uber Presidential Fellowship. I'm grateful for their support. We used several resources at the Resilient Intelligent Systems Lab for experiments conducted in this thesis, as well as resources outside the university for cave experiments. I want to thank my friends and family for personal support that I received while working on this thesis. Thank you, and I'm happy to answer any questions.